Hi everybody, today we're going to be talking about the second 2019 AP Chemistry FRQ. This FRQ is an all-in-one about the halogens, discussing bonding, electrochemistry, thermochemistry, and a little bit of equilibrium. First of all, this question relies on your knowledge of periodic trends. We know that there is increased shielding as you go down the periods, and due to this increased shielding, there is less coulombic attraction, causing the bond length to be longer, so iodine is your answer. Make sure you mention the College Board buzzword coulombic attraction because the graders love to see people use this kind of vocabulary. The most important thing in this question is to make sure that you are not mixing up oxidation and reduction potentials. Remember that when a substance is getting oxidized, you have to make its reduction potential, which is given, negative. First of all, we know that we want to get elemental bromine as a product, so we will need to make the reduction potential of bromine negative and flip the equation around. Now that we have our oxidation reaction, we can decide on a reduction reaction, chlorine or iodine. For a reaction to be favorable, the overall voltage, or E, of the reaction must be positive. And if we look at the numbers, we see that chlorine is the only viable option, because even if the 0.53 volts that is generated by iodine's reduction is added to the negative 1.07 volts, the overall value is still negative. However, we're not done yet. We still have to write the balanced net ionic equation. Since the only substances changing oxidation states are bromine and chlorine, we only leave those in and balance because they are all molecules in their natural states. When answering questions about periodic trends, the most important thing to remember is that you must address both substances in order to get full credit. So you must first start out by mentioning the intermolecular forces in both substances. While bromine has only London dispersion forces, BrCl has London dispersion forces and dipole-dipole forces. Now that we have addressed both substances, we must read the question to understand the connection that must be made. Since bromine's boiling point is higher, the intermolecular forces must be stronger. Therefore, we can answer that bromine's London dispersion forces are stronger than the BrCl's London dispersion forces and the dipole-dipole forces. This question is simply the ideal gas law. We start with our equation PV equals nRT and manipulate it to find P. Then, by doing some simple stoichiometry, we can choose any ideal gas constant since the pressure is up to us. I always like to choose atmospheres because it's simple. When we do the stoichiometry, we get our answer 1.22 atmospheres. This question gives us another easy point. We must simply write the expression for KEQ. Since everything is in the gas state, we must simply put our gas products on top and put our reactants on bottom, raising them to their molar coefficients to get this expression. For this problem, we have to break out the good old rice table. While rice tables are typically used with either concentration or partial pressure, since the question gave us percentages, I like to convert to decimals and use those percentages to make our lives easier. The reason we can do this is because the equilibrium constant, KEQ, is simply a product to reactant ratio, so we can use percentages or concentrations to find it. First, we start with 100% or 1.00 BrCl. Since the molar coefficient is 2, we subtract 2x. We know to subtract 2x because since there is no product, we must shift over to the product side. We know that 42% of the BrCl decomposed, so subtracting 0.42 from 1 gives us 0.58% of the BrCl left, or just 0.58. Now, if 42% is equal to 2x, 21% is equal to x. So by adding 0.21 to Br2 and Cl2, we get these equilibrium percentages. All that's left is to plug into our KEQ expression, which looks like this. When we put this in our calculator, we get 0.13. The final part of this FRQ is a simple summation equation. Remember that with bond dissociation enthalpy, the equation is actually reactants minus products, not the other way around. When we set up the equation, we get these numbers. When we simplify and solve for our unknown, we get 219 kilojoules per mole. Congratulations, you have completed the second 2019 AP Chemistry FRQ. I hope this video helped you and there will be more coming soon. Take care and I'll see you in the next one.